So hi everyone, my name is Carlos Lassans. I'm from Naver Labs Europe. Today I'm going to be presenting our solution for the Miracle competition of trying to extend all the tools that we have for IR in English to multilingual IR. The main goal is that we have this large set of tools for English, but can we actually use them on multilingual? And kind of giving a spoiler, we kind of can, but we have added costs when we go from like a setup that we know very well to a setup that has like new data and new languages. So my main idea when I was participating was to first try to develop some baselines. So trying first to translate all the data to English and then retrieve with the English models, and then trying using either neural sparse retrieval or neural dense retrieval, but this time in the context of multilingual IR, and finally doing re-ranking. So this slide, I'm going to be very fast because the other two teams already presented the task, but the main idea is that we had 18 languages and 2 tracks. For the non-languages, we had 16 languages with training data, and for the surprise one, we had just 2 languages, but we had no training data. And one of the things that I found most impressive about Miracle is all the work that came for the annotation, because they have almost the same amount of judgments as MS Miracle, but this time we have not only relevant documents, but also non-relevant documents, which allows you to do some other types of analysis. And most of those annotations are based on an ensemble of BM25, MDPR, MColberts, and some other values from MSETID. So for my presentation today, I'm going to be spending most of my time in the non-languages sections and even more on the first stage. So it's nice because differently from the other teams that focused on re-ranking, we mostly focus on the first stage. And then I will talk about surprise languages and some preliminary analysis that we have run to try to better understand what worked well in this challenge. So to start, we started with the zero-shot baselines on Miracle that were made by the organizers, where we kind of see that hybrids work pretty well in this setup, and that even if both models are not as strong, the hybrid of those models gets a very nice boost. So for example, just starting with BM25 and MTPR, you can get almost 94% in recall at 100. And then our first approach was, okay, can we reuse what we have from English? So the first thing that we did is that we took No Language Left Behind 200 for translation, which is clearly free to use. We were thinking about using some APIs that exist in Python, but we were not sure about the license and how to use them. We were mostly just translating back to English. And this process was not plug and play at all. So we thought that it was just, okay, we can take their model, we can try to use it, but it actually generated a lot of things when it was confused. Like it generated things like, I don't want to translate this, or other stuff like that we were not expecting. So we had to do a lot of filtering after translating. And then we applied Split++ and SemDistill, which is a model that we have been working for a while, and we have fine-tuned it separately for each translated language. And I actually don't have a good reason for why we did that. I don't remember why we don't just use all the translated languages as one, but it was probably related to some bias that we had found. Just to give a little bit of a recap on Splade, because I will be talking a lot about it, as it's the model that we are most used and the one that we use a lot in this work. The main idea of Splade is that instead of doing a dense retrieval by taking an output of the penultimate layer, we're going to take advantage of the MLM head that was trained when doing the MLM mass modeling with the model. We're going to add a log saturation, and we are going to induce sparsity using a ReLU over the output so that all the negative values are dropped. And we are going to use flops regularization that tries to estimate the activation distribution, so that the model actually creates a sparse representation and not only uses a subset of all the available dimensions. And what we see is just by adding the translation, we can get almost the same performance in MDCG at 10 as the hybrid that we had before. And the translations actually added a lot of diversity in that we have almost the same recall at 20 as we had before recall at 100. So this would make re-ranking a lot faster and a lot less cost of re-ranking, as we can get almost the same amount of positive documents, but in a way smaller subset. Then we started looking what we could do with monolingual Splade. So Due to recent submissions, we had some models in languages that were non-English that we could test on this. So we had on Chinese, Farsi, Russian, Arabic, and Japanese. This came originally from other data sets, and we actually did not want to train 16 models, but we mostly wanted to be able to compare if we were able to train one model with the 16 languages against the monolingual models that we had from before, and try to see, okay, do we need to train 16 different models, or we can just choose one that's trained on all languages? And actually, when we started this, we believed that monolingual split would be the thing that would work the best and not the multilingual one. And we were kind of surprised and pretty happy that actually using all languages to train a single model was more effective than training 16 different ones. So just a little bit of intro on what we had to do to be able to go for a multilingual split. There was actually a previous work on trying to use splades for more than one language, which is splade X, where they were trying to do cross-language retrieval. They found mostly two problems: vocabulary size and initialization. So vocabulary size, the main problem is that as your vocabulary increases, the cost of training those models increases a lot. And we also have a problem of initialization because of the log and because of other properties of splade. That, for example, if we look into the figure here, when you initialize with mbert, most of the weights are negative. So you already start getting some sparsity, and most of the weights are between 0 and 20. So using the log there, we'll still have some space, and we'll not have saturated all the values to the same place. But for example, if you start with XLM Roberta and you try to apply splades, you'll probably fail because, one, your model will not be sparse for the start. So you have to have a huge shift from starting from a model that's not sparse at all to something that will be sparse. But also, as you apply a log saturation and your values start from between 20 and 60, all your initial values will be concentrated in the same part of the space. Like, you will not have much of a difference between your minimal value and the maximum one. So training those models will be very hard. So to be able to actually train those models, what we did is that we had to calibrate the model for splade. So this is just first a recall of what is masked language modeling training. The main idea is that you have a model, you will mask some part of it. So for example, we have here, do goldfish grow, and we have mask grow. And then we pass it through the network, we get the output, we do a final full connected layer that generates the logits. And then we perform a softmax to get probabilities about which words will be used here. By doing the masked language modeling, we are actually doing document expansion for free, but we have no sparsity. So we are not we're making the model good for splade in a way that it has document expansion, but not so good in that you're not enforcing any sparsity here. One other problem is that you're using probability, and when you're using probability, you have multiple solutions where you are not sure if you're going to finish on the left or the right on the figure before. So you don't know if you're going to finish in a way that is good for splade or if it's bad, depending on which part of the distribution you finish on. And finally, the logits are not bounded. So when you do the log saturation, if you don't have any bound on the values, the saturation will make that all values go to the same space. And so that's what makes very hard to train splade on this scenario. So what we propose to try to fix this is what we call MLM plus flops. So in normal MLM training, you just take the logits and you apply the MLM loss on top of it. On MLM plus flops, what you do is that you first convert your logits to something that's splade-like. So you apply the log saturation, you apply the sparsity, and then what this is doing is that this is enforcing the saturation to work. So this is enforcing that you're in a good part of the distribution and that you're able to clearly differentiate your values. And this starts to introduce sparsity so that when you're going to train your model for retrieval, it already knows that the values have to be sparse. And finally, what we have is a tripartite loss where we have the MLM loss at the beginning, we have the MLM loss over the splade-like features, and we have the flops loss at the end. And each separate part of this loss is trying to do something different, where the first one is trying to avoid collapse. So one thing that can happen when you introduce sparsity is that you can collapse all values to 0. And the idea is that by keeping the first term, you're ensuring that you always have a loss that you can optimize. The second one is performing sparse document expansion. So you're not only learning to enforce saturation and introduce sparsity, but you're also learning how to perform document expansion with sparse logits. And finally, the flops loss has two parts here. One is that's going to bound the values to being a good part for what we need. And the second one is that's going to balance the terms. And this is something that's very important in a multilingual setting, because what happens a lot with MLM when you're in a multilingual setting is that you're going to focus mostly on the languages that have the most tokens. So what happens is that your model will kind of learn some priors that if he's not sure of like which language or what's going to come next, it's going to give high values to common terms. And the idea of the flops here is to avoid collapsing everything to the common terms, but actually spreading over all the terms that you have in the vocabulary. So our first try with msplayed was what we call msplayed small and msplayed large. We were going to use a vocabulary from XLMR, which is a very large vocabulary, and we were going to remove English from training because we wanted to avoid biasing the model to the largest language that we had. Actually, trying to use XLMR base was too big, so we could not train on our servers, and we had to actually go back and train from scratch a model that was half the size, so just 6 layers. And this had actually 3 steps. So training from scratch with MLM plus flops took 5 days with 4 A100s. Then we fine-tuned with mMarco, which took 2 more days. And then finally, fine-tuning on Miracle is way faster, just took 2 hours. It was actually better than the first hybrid that we had, but it was not practical to use. Like having a vocabulary so large made it almost impossible to work with this model. So what we did is that we did a second try, which we called smaller tokenizer, and we actually generate the vocabulary for the Miracle corpus. The idea is that having a dedicated vocabulary will help us to actually have more full words and less and have less of a need to actually expand tokens and to have to break words into multiple tokens. We do the same training as from the previous slide, but now we have half the costs. And this actually improves a lot over the previous training because it's not only less costly, but it's also easier to train the model with less tokens. So what does that makes us for the dev set? What we see is that all 3 multilinguals played actually improved over the translations, with the smaller tokenization having the best results out of the 3. The recall at 100 of the msplayed small tokenizer is almost the same as the hybrid baseline that we had at the beginning. And by adding these models, while they have like better results individually, they actually are not contributing that much for the hybrid. Like we're starting to saturate due to the amount of models that we use. So finally, we also look into dense models. So for now, we have been looking into the models that we use in English in a multilingual setting. So it's normal to not only look into sparse neural retrieval, but into dense neural retrieval. We actually were lacking a fine-tuned dense model. We have been only using MDPR that was 0 shot in Miracle. We perform the same training as msplayed. So we do first fine-tune on mMarco and then fine-tune on Miracle. And then we do a comparison to msplayed. So mcontriver and mcolbert, they are using a much larger pre-training, and they are performing all around the same on the 15 pre-trained languages. The main difference is actually English, where we did not train our model on English, and those models had been pre-trained on English. So we wanted to take a look in how these models are gaining against BM25 to be able to say, okay, where is the advantage? Are we getting the same advantage over all languages, or is there something different? And what we kind of saw is that even by taking all these precautions, the splayed model is actually still preferring the more Latin languages while mcontriver is better on non-Latin scripts. And if we look into all the models that we generated, what we get is that we almost saturated the end. Like mcontriver was a little bit better than msplades, and mcolbert was a little bit better than mcontriver, but mcolbert is a lot more costly to run than mcontriver. And if we look into the hybrids, we started with the hybrid from the organizers. We added the translation, which improved a lot. But after that, each addition of models actually improved less than before. So by adding the splades, we got 4 extra points. By adding the dense, we got 1.7 point extra. And by carefully selecting which models are used for each language on the dev set, we got our final model, which has an NDCG at 10 of 77.2. And that has a recall at 20 that is better than what we had at recall at 100 before. So that makes us able to re-rank a way smaller setting and have a potential same result. So now that I finished talking about the first stage, let me talk about the re-ranking on the known languages. We mostly based our re-ranking on the rank T5 encoder only model. We would fine-tune first on mMiracle and then on Miracle, as we had done on the first stage. The main idea, as before, is to kind of take the models that we know that work pretty well on English and use their multilingual pre-trained models on a multilingual setting. It was actually very difficult to outperform our first stage hybrids. Like even when selecting the best top K from dev, looking what works best, top 10, top 20, or top 100 re-ranking. But ensembling still leads to improvements, especially if we use a lot of different initializations for the re-ranker. And these are kind of our final models. So our first stage hybrids got a 77.2 NDCG at 10. Our best re-ranker gets 78.6. But what we see is that we are not able to improve much over the first stage with our re-ranking. And if we do a hybrid, if we use our 2 best re-rankers and our first stage, we get to 80.4. And if we push a little bit further, adding all the models that we have, we get to 81.0. So this was mostly our solution for the known languages. It's kind of hard to say what really worked best because we had a lot of brute force at the end, because as we used all the models that we trained, it's hard to actually know which part was that worked the best. So if we look into the test B results, what we did is here is that we consider that our method was the baseline and we plotted the others in relation to ours. So everything that goes out of the circle means that we are being outperformed on those data sets. And if it's not going outside the circle, it means that it's not being outperformed. And what we see is that for 12 of the 16 data sets, we got the best results. But for the other 4, especially on Telugu, Spanish, Bengali, and Indonesian, we got worse results than other teams. And we are not so sure why, because we were expecting something that would be possibly linked to the language origin or to the size of the language. But at the end, we have from very low resource languages to very high resource languages. So we were not able to actually understand if there was a pattern here between the performance of our model and the performance of the other teams. So next, let me talk about what happened in the surprise languages track. In the surprise languages track, we added 2 extra languages, German, which was a very high resource one. It was actually the 2nd largest corpus of Miracle, and Yoruba, that was kind of like the opposite. It was the smallest corpus on Miracle. They had no training data, so we had to mostly reuse previous models at 0 shot. But as we had mMiracle, we also tried training a monolingual German splade to have an idea of how well it's performing against the rest. So if we look into the surprise languages track and our first stage models, here we have all the models that we had used on the known languages and their performances. As expected, the multilingual splade that was trained only on 15 languages, it was not able to transfer that well to German. We were kind of surprised that it actually worked a little bit well on Yoruba. And actually, the translated model worked pretty well on Yoruba, like outperforming all the other models by a large margin. And if we add the hybrids, we have almost the same thing as we had before. Like each successful model that we add actually increases the performance, with the largest gain coming from the very beginning when we add the translated splayed on top of the organized hybrids. And by adding msplayed here, we are actually making the models worse. So when we use the best performing hybrids over the dev set, we mostly exclude the msplayed from this. And for the surprise languages track on the re-rankers, actually here we saw larger gains compared to the first stage. So as we just saw on the known languages, there was almost no gain on the re-ranking side. Here on the surprise track, there was a lot more gain. One thing that we imagine is because the re-rankers, they are larger models than the ones that we are using for the first stage. And they are probably able to learn more from their pre-training, and they are able to keep more knowledge of the languages that they are not fine-tuned into. And actually something that quite surprised us is that we almost fell out of the top 10 on the dev. And then we started throwing more models to see if we could do something, and actually did not really improve. Like what kind of helped us was kind of like the shifts between the dev and the test B. So these are the final results for the surprise languages track, where we got first place, but we were 9th on the dev. For example, our German models before were not ranking very well, but on the test B, they did. And as before, Yoruba, we had the advantage of the translated model that really helped for that language. So finally, like participating in a competition is very nice. Winning is good, but like understanding why we won is something that we are still trying to do, but that's sometimes is very hard. So this is kind of like our first attempt of trying to understand what happened. And actually, one question that we had is, did we make the problem harder for us? Because every time that you have an evaluation, especially information retrieval, you're actually trying to model a system that came before. So on Miracle, you're mostly modeling a system that has a hybrid between BM25, MDPR, and Colbert. And at the end, it's re-ranked by a human. And something that I don't have on the slide here, because I just reflected on it today, is that this is kind of different between test A and test B. On test A, you have BM25, MDPR, and Colbert, but you also have the relevance judgments from Mr. Tidy that don't come from this model. So you have kind of like a separate model helping you get the judgments. And when you are on test B, you only have those models. So you kind of have a shift between what can be a positive on the test B and on the test A. And everything that's not found by those systems will be ranked non-relevant, even if it could be. And so this kind of created a question for us. Was it worth it focusing on the first stage, or should we have just used the first stage that was given to us? Because that was kind of like what the system that we had to model uses. And the first thing that we have is that the actual number of judgments at 10 from our model is smaller than the judgments at 10 from the first hybrid. So even if we have a lot more recall, and even if we have more NDCG, the amount of judged documents is smaller. So we have potentially more false positives than the hybrid. So what we did is that we did a case analysis on the French language. We took the first place documents. In French, you have 342 queries. We actually have relevance data for a lot of them. You have 217 positive, 93 negatives, and just 33 or 10% of the queries are without relevance. Out of those 33, only 5 are not in the top 200 of BM25, and only 2 are positives. So it's a very small subset of the non-relevance that are positives in this case. And actually, what kind of surprised us was the opposite. From the ones that are on the top 200 of BM25 and MDPR, a lot more are positives. So this actually means that by focusing on the first stage, we're making these documents appear more, and we are making it easier for rankers. And for now, we believe that was worth it focusing on the first stage. Like by making these document surface, we got a little bit better results at the end. We actually wanted to do on all of the top 10, but it would be more than 1,000 judgments to do. So at the end, we were happy just doing for the first place. So in conclusion, actually, it was pretty nice to see that all the models that work in English work in multilingual. You have some pain points of trying to use, like Splade has to do some very specific stuff. For Contriver, we have the advantage that the authors train both the Contriver and mContriver pre-trained models. But we definitely need better re-rankers, like especially for what we did. Like we had a lot of gains on the first stage, but our re-rankers were very, very poor, especially compared to maybe the other teams in the competition. And we actually believe that it was worth it to work on the first stage. So I think that's all. Thank you.